of a component, cost of printing, material consumed for printing, time taken for printing, mechanical property of the part. So multiple output are affected based on support structure. So you have to be very cautious when you do a part orientation. So to guide you for having a better part orientation, set of guidelines are available. For example, the slide which I have shown here, it shows the set of guidelines. If you follow the guidelines, you could able to achieve the better part orientation. For example, maximize number of perpendicular surface, maximize number of up-facing horizontal surface, maximize number of holes, maximum number of curved cross-section drawn in a horizontal plane, maximum the area of surface, maximum the number of slopes, minimize the number of sloped surface, minimize the total area of overhanging surface, minimize the number of trapped volume. So these are some of the guidelines which you can follow to optimize the support structure. To understand these guidelines in a better way, in the subsequent slides, I'll be demonstrating with some. So you can see the impact if I do a maximum number of perpendicular surface, how it is best part orientation. So we will see all these guidelines with an example now. Okay. So I hope this part is visible to everyone. That is, if you look at the two diagram, just for demonstration the number of rules, how the rules are going to have an impact. We'll see with the diagram. So the first rule is maximum perpendicular edge. So here I have taken two parts. The blue color region is your table. On the part of the table, you have a part. So the pink color contour is the part model, CAD model, and a green color contour is the layer. So this model will be printed layer by layer. Now, this is first orientation and this is the second orientation. Same model, but I am going to print in this direction. That is, let us say it is 90 degree. I have rotated the component for 90 degree in counterclockwise direction. So the two, here you require a structure because this surface is downward facing surface. As the surface is facing downward, you require a support structure here. But if you look into the first case, you doesn't require a support structure because this surface will get support from this will get support from this, and the top surface will get support from this. So this dissipate two example. When you have two different orientation, how the orientation is going to have a support structure. Now this we can do it manually, but how does the computer understand? Because computer read only geometry, right? So the first rule is maximum perpendicular edges. So you have to increase the maximum number of perpendicular edges. So if you look into the table, this is a table. Blue color line is the table. So how many perpendicular edges are there? So this edge is perpendicular to the table. This edge is perpendicular to the table. This edge is also perpendicular to the table. This edge is also perpendicular to the table. So if you take first module, there are 4 edges of a model perpendicular to the table.
Sir?
Yes.
Sir,
Yes,
I am unable to see the slides, sir.
no, but could you able to see the PDF? No, I did open the PDF.
Oh, okay, sir.
No,
Okay, sir.
could you able to see the pink color contour model, like L-shaped model?
Yes, sir.
No, sir. I just see a blank screen. That's it.
Maybe. How about others? Others could you able to see?
Yes, sir.
Maybe I'll do the sharing one more time.
Okay, sir. Thank you, sir.
Okay. So could you all able to see the L-shaped model? L-shaped model.
No, I'm still unable to see it, sir. Sorry.
Maybe some. How about others? For others, it is visible. L-shaped model, pink color.
Yes, sir.
Yes,
Okay,
sir.
no, it might be because
Yes,
of
sir.
network issue. I'll share the recorded video. Okay.
Okay, now I'm able to see it, sir.
Okay. No issue. So if you look
Okay,
in
sir. Thank you, sir.
to the first model, there are 4 edges perpendicular to the table. If you look into the second, 1, 2, 3. So only 3 edges are perpendicular to the table. So this is how the computer will understand, because for us, we can able to see which orientation is best by manual visualization. But if you have very complex component, because in additive manufacturing, we are going to print a complex component. So multiple surface, you cannot do visualization automatically. So computer has to compute, and it has to tell which is the best orientation. So how the computer will identify? It will identify number of triangle, because we are going to convert a surface into connected triangles. So it will identify how many triangle or how many surfaces are perpendicular to the table. So it will keep on rotate a component, and at which orientation the number of faces or perpendicular faces is higher, that orientation is best. So this is one of constraint. Would you all able to understand this point? Number of perpendicular surface should be higher to minimize the support structure. Is it fine? Can I proceed to the next point? Yes.
Yes, sir.
Okay. The second point is maximum horizontal up-facing surface. So let us see the horizontal surface. So this is 1, 2, 3, right? So there are 3 horizontal up-facing surface, and one is inclined, which is also not good. So if you look into the second part, you have 1, 2, 3, but you have a downward facing. So whenever you have a downward facing, obviously the downward facing requires a support structure. So this is another way in which you can see the you can computationally you can manipulate the path. So make sure that there are more number of horizontal surface which are facing upward. Try to minimize the horizontal surface which are facing downward. So this is another criteria which computer will use, because based on geometry and with respect to the table geometry, computer can automatically calculate whether it is parallel or inclined or some angle. So that information will be fed into the program, and it will calculate number of faces at 90 degree, 0 degree or 30 degree, and based on the multiple computational iteration, it will able to identify which is the best orientation. Minimize overhanging feature. For example, if your design allows you, for example, this is the best orientation, maybe in terms of support, it is not advisable, but because of some strength criteria, you have identified this is the best orientation. So instead of using support, you try to minimize it, try to embed this component into the part itself, or try to make it as a angled or chamfered component so that it will be self-sustainable. So someone asked what is the overhanging angle. So certain angle can be self-sustainable. If you have a 90 degree flat or 0 degree flat down facing, you require a support. But if it is an inclined surface, you have to change the design. You have to change the design itself to avoid a overhanging feature. So try to avoid a overhanging feature. Yes.
Thank you so much.
Hello.
Okay. Mm,
Okay.
Thanks.
The third part is another another rule is
Thank
if
you.
if we have a circled feature, circle
Ah,
component. So if you have a circular component, for example, you take this case, I have a cube. At the center of the cube, I have a circle. So if I want to print this component layer by layer, if I'm going to print this component layer by layer, this surface from this point to this, it will be a curved feature. So you could be able to see the staircase effect. Could be able to see the staircase effect. When I have a straight edge, there is no issue of staircase effect. When you have a curved edge, and if you are trying to print a curved edge along the build direction, so this is the build direction. So if you try to print a curved edge along the build direction, you have a staircase effect. So what you can do, you can tilt the part in such a way that the circle is facing upward. So if you make a cube, you have a cube. At the center of the cube, you have a cylinder, hollow cylinder. So instead of fabricating a cylinder in this direction, you can fabricate a cylinder in this direction. So I have kept a second model. So if you look at the second model, the circle is facing upward. So when you see the top view, front view of a circle, it is when you see the front view of cylinder, it is a rectangle, right? You might have done a top view and front view. So if you draw a cylinder in top view, it is circle, but in front view it is rectangle. So in this case, along the build direction, you can avoid a curved edge. So the curved shape is built only on XY plane, and the length of the cylinder is printed in Z axis. So this is the another way in which you can avoid a staircase effect, or you can improve the surface finish of a component based upon part orientation. So make sure that you are printing the cylindrical feature axis which is along the build direction. So if there is a circular feature, definitely the circular feature will have an axis, and always the computer will try to orient the axis perpendicular to the table, or it will try to orient the axis along the layer by layer addition. So this is how the computer will automatically manipulate. It will see the axis because computer can read the axis of a circular feature, and computer can calculate the angle between the axis of the circular feature, and it will try to orient the part in such a way that the axis is perpendicular to that. So this will help you to avoid a staircase effect, which will have an impact on your surface finish. And another critical point of this is, if you have a curved feature, if you can see that the top, right? So on the top, you require a support structure. When you print layer by layer, you require a support structure on the top. So that can also be avoided by using this feature. So from this point to this point, it doesn't require a support structure. But when you try to print the curved feature, this cylindrical surface is also facing downward. So it is a downward facing surface. So that will generate a support structure. So another important point is you should have a maximum area. For example, I have a CAD model which will be having an additional feature like this, the triangular part which you can see. So make sure that the maximum surface is at the bottom. So in this case, the maximum surface is at the top. So in terms of maximum surface, this is best. In terms of circular feature, this is best. But if you print it with this second orientation along with the feature, you require support for all of this region, right? So you have to decide whether you are going to give a constraint on support, or you are going to give a constraint on surface finish. So based on the requirement, you can see the part orientation, best part orientation. Another critical point, so as I have mentioned about staircase effect, I have trapezoidal shape which want to be printed using additive manufacturing process. So when I print, all the straight edge will print properly. So this edge is straight. This edge is perpendicular to the table, so you do not have any issue. When you try to print a slope or inclined edge to the table, definitely this how the printing will take place. So this white color region is an error. So this error effect is called a staircase. So this will be like a staircase. The green color contour is your actual model, but the printing will display like this. So this is how your printed part will look like. So the printed part will have a staircase effect. How to optimize that? For example, you need this surface at high finish. Assume that the angle between these two edges is around 45 degrees. So what you can do, you can rotate a part in such a way that this surface will be vertical and all other three surfaces will be inclined. Though it is inclined, all the three surfaces will have a staircase effect, but this surface will have a smooth finish. If this surface is your functional component, then according to the angle, you rotate a component to get a better finish. So this is what the constraint which is explained in the rule, what I have mentioned earlier. So these are the rules which are mentioned in the part orientation constraint. So most of the software have this constraint. If you do it automatically, or if you define the value for this constraint, automatically this software will be oriented. So that will add a value to the best path orientation, which you can automatically predict through the software. So you can, if you are comfortable with topology optimization or any optimization procedure, you can integrate the optimization procedure with a constraint for a CAD model with respect to specific additive manufacturing machine. As of now, we have discussed only FDM machine. You can also see other missions. Other missions have different constraints, so you can use those constraints as a constraint for part orientation. Come up with a new algorithm. So that is all about the part orientation for support, part orientation for